Okay, so in this video I'm going to walk us through the theory behind Word2Vec, and then we're going to dive into uh, the library that actually execute all this theory in code. And so uh, we have our word that we're going to create embeddings for, and we have a transformation over here, so like sort of mapping through the one-hot method. And what we get, as you should know by now, is this vector representation of that specific word by 1. And we're going to multiply this vector by the matrix of the representation of the center words. And what this will give us, this is basically just, this whole thing is just a selection process. This is like, we can think of it as using the identity matrix to kind of flesh out the center word. And once we get this center word, what we want to do now is we want to end up essentially with a vector of probabilities that in which each probability is assigned to a specific word. So we have we got the center word, and we can which is noted by T, and we're going to multiply this this matrix by, or vector more accurately, by the matrices of context words. So I just followed the lecture as the told that 3 are much more than 3. Probably have more words in the corpus. So the context words, and we get this this vector that is the dot product of the word after it was fleshed out by the one-hot and the center words times the context words. And we're going to take this, and in order to generate probabilities out of it, we're going to use the softmax. And the softmax is doing 3 things. It's doing dot product, and the second thing, all right, I hope you got it, it's doing exponentiation. So it's going to take the dot product from here, it's going to exponentiate it, and then it's going to normalize it by the sum of those exponents. And by doing so, we get a probability because this normalization turns this vector that we had of the, or this dot product that we had, into a probability between 0 and 1. And we arrive at vector of probabilities. What we can do with this vector is that we can compare it to the ground truth. So the ground truth is vector of 0s and 1s. So it's, again, the localist representation. And if we're doing well, then we're going to have very low probabilities that the word is not the right one. We're going to have high probability for the right word represented by 1. And I just want to emphasize the premises that this whole model is built on, because we all know that the model is as good as its premises or its assumptions. And so here are some blanks. So there's only one way to do what. So this has to do with the distribution, or the probability of the conditional distribution of the context words given the center word. Well, it basically gave us a pretty big hint here. And a word is best described by its neighbors, and we can even add 2 over here, because this assumption helps us generate 2 representations, as you can see in the video, noted by U and V, and a dot product. And a good question to ask is, why we use dot product, for example, here, or here. I think here it makes more sense, but why we use dot product all those times for softmax? So what we get, and as we explained, the dot product, just multiplication, is quite useful when assessing similarity, or when we want to sort of flesh out something, and when we have something similar to the identity matrix, it will work like a filter. So there are 2 different reasons of why we use it. And well, so let's do some hands-on practical implementation using the Jensen library and the Word2Vec function it provides to do what we did on the whiteboard. And so we take our data after we import Word2Vec. We take our data. By the way, this whole thing is from Machine Learning Mastery, which is a really great resource. You can look at Jensen if you want as well. I put the link here. Back to the data, we're going to train the model. So the training basically does everything we covered on the whiteboard. It's doing the localist 100 representation. It's going to do some dot products with the context words, with the surround, the basically all words but the sender words. It's going to flash out the sender word that way. It's gonna do dot product again, and then it's gonna take and it's gonna softmax this dot product to achieve a vector O fill in the blank probabilities, and it's gonna compare those probabilities. This is the way we learn, and you can watch the end of the Stanford lecture. It's gonna take the softmaxed probabilities. It's gonna compare them with the ground truth to compute the delta. So it's going to learn that way, and it's going to optimize the parameters based on this comparison. And so we achieve a model, we print the model's words, and we can access some vectorization just like the basic functions. So you get to play with it. You can save and load it. And this is basically the data that the model encompasses, and we can get an idea of what the relationship between the words if we use PCA. So we're all familiar with principal component analysis. So we're going to have to use two components or at max 3 so we can actually visualize it. And we're going to PCA it and we're going to plot it. We're going to see the relationship between the words. And so now the words are each word is a vector, and this is the embeddings. And surprisingly, we see that 156 is very far from ML. And that's going to be my question for you. How does this happen? And we see that we and now are quite close to each other, but we see that now and no is quite far. So, yep, I encourage you to put your own sentence over here, play with it, and if you're interested, you can go to the link provided and look at the source code as well. And that's it for now.